there. What I want to cover in this video is just the basic theory of what calorimetry is, and just to review a little bit about enthalpy. The word enthalpy comes from this Greek word called enthalpine, which means to warm. So I know in the lecture videos I talked to you about measuring delta H or calculating delta H using bond energies. That's a purely theoretical way to do it. This is a experimental way of measuring delta H. And the way we do that is we carefully weigh a sample, we measure its temperature change, and then we assume something about its specific heat, which I'll get to in a moment. But in calorimetry, what that means is we're going to measure the heat gained or lost at constant pressure. So heat, which is Q, you have to learn some of the symbols here. Lowercase q means heat. That is the when that's measured at constant pressure, we call that delta H. So we call that enthalpy change. And that's okay because most reactions, if not all of them, are always run at constant pressure. We run in open vessels in laboratories, so that's fine. So delta H less than 0 is called exothermic. I know a lot of this might be review from your lecture videos. That means heat flows out of the system. So I'm going to run through some of this kind of quickly. Endothermic means delta H is positive. Heat flows into the system. It's very important that you keep track of those directions. It's all about direction in thermochemistry because you have to keep track of the flow, which involves a negative sign in these equations you'll see. But the units we use are joules per mole, kilojoules per mole, calories per mole, kcal per mole. The one we're going to use is joules per mole. Recall that 1 calorie is 4.184 joules. We use calories in this country, joules in Europe for on the labels of food. So what we do know is that when you add heat to something, you cause its temperature to change. The more heat you add to something, the more its temperature changes. That seems pretty obvious, but that will help us understand what specific heat is. So the higher the temperature means you're adding more energy to something. But not all substances respond to the change in temperature equally. Some change a lot when you add heat. Some change a little bit. So the way we usually do that is we pick 1 gram of substance. It can be solid, liquid, or gas. We add in some energy in the form of joules. Could be heat. It could be a flame or something like that. But let's just say you change the temperature from 25 degrees Celsius to 26 degrees C. And you've carefully measured the mass. If you carefully measure the amount of heat you added, you could calculate what's called the specific heat. So here's some notation that you need to use. It's lowercase c sub s. That's called specific heat. There's a term you're going to see that's a capital C. That's heat capacity. It's different. Lowercase c sub s is specific heat. It has units of joules per gram degrees C. So it's proportional to the amount of heat you give to an object per its mass and change in temperature. That's why they're in the denominator. So in notation, that's Q divided by m delta T. You add some energy to something, you cause a certain amount of that substance in grams to change by a certain amount. And when you rearrange that equation, you get a very well-known equation that you're going to use. It's Q equals mc delta T. C sub s just means, the little subscript s means specific heat. So for water, for instance, what they did is the way to measure the heat capacity, the specific heat of water, is carefully measure, let's say, 50 grams of water. A lot of these numbers are measured at room temperature experiments. So room temperature is about 25 degrees. Let's say you add in some energy. You could measure that energy, and you would measure about 209 joules of energy would be needed to cause 50.0 grams of water to change by 1 degree. 25 degrees C to 26, so it's going up by 1 degree. If you plug those values into that equation, into this equation here, you can calculate that the specific heat of water is 4.18 joules per gram degrees C. More precisely, it's been measured to be 4.184 joules per gram degrees C. I looked on Wikipedia, it's slightly different from that, but this is the number that we always use in chemistry class, so this is fine for us. I'd like you to use this number, 4.184 joules per gram degrees C. What does that mean? Well, it might be more meaningful to you if you looked at how that number compares to other substances. Water has you'll see a much larger specific heat than most substances. Aluminum and iron, which are metals, have very low specific heats. Carbon dioxide has a pretty low specific heat as well. So that's unique about water. It's a very high specific heat. That means water retains heat very well. It retains heat very well, and it loses heat very well. And it also takes a long time. It takes a lot of energy to heat it up. If you take a piece of aluminum foil and stick it in a really hot oven, you can pretty much immediately grab that once it's out of the oven because it has a low specific heat. That number is a reflection of the fact that aluminum metal loses heat very fast and it heats up very fast, as does any metal like iron, and I think they all kind of have low numbers. Water with a high specific heat just means, yes, it takes a long time to boil a pot of water, but that pot of water will stay hot for a long time. That's why the oceans give a temperate climate to cities near an ocean, because the ocean is like a heat sink. It holds on to that sunlight energy that it absorbs all year very, very well because of the high specific heat.